Okay, another example of using binary variables in a linear program. This one has to do with planning production to try to meet demand, and trying to decide what sort of shift to use, whether a normal shift or an extended shift. And then once the shift is decided, then how much to produce. So go ahead and pause the video, take a read through the problem description here. Think about what are the variables, and then can you come up with the objective and all the constraints? So give it a try on yourself. Otherwise, unpause when you're ready and we'll talk through it. So looking through here, first want to kind of highlight we've got demand here that varies by month. And so that's going to be a parameter of the problem. But then let's go ahead and define our decision variables. So we're going to have quite a few different decision variables defined in each month. And maybe I'll actually start with kind of the first ones, and then we'll come back and add more decision variables as we sort of need them to accomplish what we want in our constraints and in our objectives. So first we'll start off with one we'll call normal of M. Essentially, this is going to be a binary variable, and it's going to answer the question, should we do a normal shift in month M? And so let's see, we'll say this is a binary variable. And the question that it's asking is, should month M be a normal shift? Okay. We'll do the same thing with extended. In month M, also a binary variable, and it will record whether that month should be an extended shift. Okay. So this will record whether it's normal or extended. You'll notice reading through it, we have the potential to not have any shift at all, and have no shift. And so we could create another variable, maybe call it furlough if we're kind of letting the workers off for a month, and making them unemployed. But if we're not doing a normal or extended shift, then we are in the furlough. And sort of it's going to be the opposite of these two together. So we'll sort of consider that in our model as well. Okay, we're going to need a variable that's going to track how much we produce in a month. That's going to be a continuous variable. And that's going to be how much to produce in month M. Okay. And then we're allowed to carry over some inventory from month to month. And so we'll need a variable to track that inventory from month to month. Also going to be a continuous variable. Note, we might want it to be integer, but our units, we're dealing with so many units that rounding isn't going to be a significant issue. So we're going to consider the inventory variable to be at the end of the month. Okay, so sort of after we've produced everything that we're going to produce that month, and after demand is consumed everything that we consume in that month. Okay, we'll add one more variable in just a little bit, but we'll come back to do that. Okay, so let's jump down to the objective. And let's kind of think about what contributes to the objective. In this case, we want to minimize the cost of running the shift, okay, or running the factory, okay. And let's think about what influences that cost. Essentially, we're going to have costs every month. We've got a certain cost for running a normal shift. We've got a certain cost for running an extended shift. And so let's see, it's 100,000 times whether or not we have a normal shift, and 180,000 times whether or not we have an extended shift. Okay, and so those are sort of flat costs no matter how much we produce. Sort of we made union agreements, and so we're paying that much to have the workers there, whether or not we use them to their full production or not. We're also charged a carrying cost on holding extra inventory. And so that's going to be 2 times the inventory amount. And then if we read through here carefully, we'll notice that there's this extra charge of 15,000 that's assessed if we change from a normal shift to an extended shift. Okay, and so to capture that, we're actually going to introduce a new variable. So I'll say plus 15,000 times change M. Okay, so let's go ahead and define that new variable. We want this change variable to record whether or not we change from a normal shift into an extended shift. So this is binary, and this is essentially a kind of Boolean operation of normal in the previous month and extended in the current month. Okay, and so this is going to be kind of a combination of these two variables. So if both of these are true, then the change variable is true. If either of these is false or both of them are false, then change will be false. Okay, and so we'll have to create a constraint that combines these two variables into creating that and scenario. Okay. And then we're going to essentially sum all this from m equals 1 to 6. So we'll add up across all of the months. So this is kind of the charges for a single month, and then we add them up over all 6 months, and that will give us the total cost of running the factory for those 6 months. Okay. Now, let's go ahead and kind of talk through what constraints we're going to need. Some of the constraints are going to be things that kind of connect with things in the paragraphs up here. Some of them are just going to be how do we implement some of the relationships between the variables. Specifically, how do we implement a change variable that actually has this relationship between normal m-1 and extended in month m. So let's work through them one at a time. First one is probably, our first two that we'll look at are the limits on production. And so looking at this, if we're doing any production, then we need to produce at least 2,000, and then Depending on the type of shift we do, we have different limits on how much we can produce. So let's see, a normal shift can produce 5,000 limits, 5,000 units, and an extended shift can produce 7,500 units. And so before, we've sort of kind of talked about how sometimes you have pairs of variables that work together, a binary and a continuous. Sort of both these binary variables work together and are kind of paired up with this production variable in telling us, are we having a shift at all? And if so, what are the production limits during that shift? So let's start working through those constraints. First, we'll start with the minimum production. Okay. So for minimum production, we need to produce at least 2,000. And so we can think of produce in a given month is going to be greater than 2,000. But this would say every month we had to produce 2,000, even if we weren't doing a shift. And so what we're going to do is we're going to take this 2,000 and multiply it by whether or not we do a shift. And so if we do a shift, we're either going to do a normal shift or an extended shift. And I will say we'll need to add a constraint a little bit later that we can't do both. Okay, and so we're never going to have both of these being one, but this will kind of push up the 2,000 to give us the minimum production if we have either a normal or an extended shift. And this would be for m equals 1 to 6. Okay. Now we can think about maximum production. So that maximum production will be 5,000 if there's a normal shift. And so we can do 5,000 times normal shift plus, and it's 7,500 if it's an extended shift. Okay, and so if we do neither shift, then both of these are 0, and that forces production to be 0. Okay, and if both of these are 0 up here, then production is greater than or equal to 0, and this would force it to be equal to 0. And so if we do neither shift, we're forced to exactly make 0 product, which is what makes sense. And this is for m equals 1 through 6. Most of our constraints are going to have that m equals 1 to 6. Next up, let's go ahead and say that we can only do one type of shift. Maybe should have started with this one. Only one type of shift. Could possibly do no shift as well. And so that's going to be, we're going to treat normal and extended as mutually exclusive. And so if two things are mutually exclusive, you add them up and then say less than or equal to 1. Okay. If they're mutually exclusive and you must do one or the other, then you do equal 1. In this case, we allow for no shift so that we are going to enforce that that's less than or equal to 1. And that's going to hold for all the months. Okay. So we're producing units. Now we want to kind of think about the flow of the units in sort of our inventory model is that we're consuming some units in meeting the demand. We're producing some units that are kind of adding to the supply. And then we have the inventory from before. And so I'll kind of label this as inventory flow, and I'll draw maybe a little flow diagram of a given month. And so in month M, we have inventory. I didn't leave myself quite enough room. From M-1 going in, we've got inventory of that month coming out. We've also got the demand going out. And then also coming in is however much we produce. So that month's production, the last month's inventory flow into a given month as far as number of products, and then demand and the current month's inventory flow out of a given month. Okay, and then we should also note we start off with inventory in our model, and so we'll call that sort of inventory 0. And there are 3,000 units of inventory from the month before the 6 months that we're looking at. Okay, so anytime you got something that looks kind of like a flow diagram and you've got this same kind of picture at each of those nodes, then you can write a flow equation where the inflow equals the outflow. And so the inflow is inventory M-1 plus produce M equals inventory in the next month plus the demand. I will point out this demand is the demand, that's a parameter, not a variable. The other 3 of these are all variables. And in month 1, this is going to reference inventory 0, which is that 3,000 there. And so this is for M equals 1 to 6. Okay, that's our inventory flow constraint. Sort of saying no, everything's accounted for. Okay. In addition to that, also still on the subject of inventory, we want some inventory at the end. And so they asked us for final inventory. Essentially, they said we want inventory at the end of month 6 to be at least 2,000 units. They don't want to be completely out of stock at the end. Okay, that takes care of most of the normal stuff. Now, the last thing that we're left with is implementing something that will force this change variable to behave how we want it to. Okay. So in the tips and tricks video, I mentioned sort of Boolean operations. Here's an example of where they come into play. If you were just kind of thinking of Boolean operations from a kind of computer science or math perspective, these ands that we sort of wrote here are usually represented as multiplication between this Boolean variable and this Boolean variable. And if you think of them as 1s and 0s, it would work out exactly how we want to. But we're doing linear programs here, even though we're dealing with binary variables now. And there's certain advantages to keeping the model linear in the variables. And so we can't do multiplication between variables. We can multiply parameters and variables, but not variables with variables. And so we want to avoid that. And so there's a little bit of a trick on how to do that to kind of make this relationship between change and these 2 variables without kind of multiplying the variables. So I'll call this one as switching. And the way to implement it is that change M is going to be less than or equal to the average of the two variables that we're interested in, which is normal M minus 1 plus extended in month M. Okay, and then we get one greater than or equal to constraint. And it's greater than or equal to normal in the previous month plus extended. Oopsie. Minus 1. Okay, let's think about what this does. So if both of these are, or really if either of these is 0, or both of them, we're either going to get 0 on the right-hand side or a half on the right-hand side. And the only binary value that's less than a half is 0. And so that forces change to be 0 in that case. On the other hand, if they're both 1, then this is 1 plus 1 minus 1 is 1, and that forces change to be 1. So only when both of them are 1 does change get forced to be 1. And if either of them are not 1 up here, then change is forced to be 0. Okay. To be honest, change wants to be 0, right? When we look at the objective, we're minimizing and we're getting charged a cost to change. And so truthfully, we actually only need the second one of these constraints in our problem because the optimization will essentially push it down to 0, which is what this constraint is doing. And so if it can be 0, change is going to try to be 0, and we only really need to worry about pushing it up. If you don't want to think about your kind of modeling as much, you just include both constraints, and then change will behave exactly like the and of normal M minus 1 and extended M. So that's all the constraints that we need. Let's go ahead and implement this in R and see what the solution is. Okay, here we've got the code in R. Here we've got the demands that we're bringing in and kind of just computed the number of months here. Here are all our variable definitions: normal, extended, change, inventory, and production. First three are binary variables. Inventory and production are continuous. We've got our objective value that we're trying to minimize here. And then we've got our minimum production, maximum production, only one shift. To implement this sort of right in R, we got to split the first month off of the flow equations from the rest of the month to kind of deal with this 3,000 from month 0. And so here's sort of month 0 and production in month 1 flowing into the demand and the inventory coming out of month 1. And then the rest of the months we can do this, and we don't have to worry about this M minus 1 giving us an index out of bound. And so notice here that now months is 2 through the number of months. And so that's one thing to be careful about. Oftentimes when you've got a bunch and you can kind of say for each in the math, oftentimes in the computer code, you need to maybe deal especially with the first one and maybe especially with the last one, and then you can let it run automatically for the ones in the middle. Okay. Similar thing we had to do for the change variable because normal 0 is true. That becomes this equation that it's going to be +1 for the normal 0, and then the -1 cancels out. And then here's for months 2 through 6. And I only did the one constraint. So I only did the what I kind of think of as the push up constraint that forces change to be 1 if we're doing both normal in the previous month and extended in the current month. And then the final inventory, and that should be it. And we can go ahead and run this. And here's our production plan. It's maybe not the easiest to read. Our objective value is that it'll cost us 943,000 to run the plant. And here's sort of all the values. Let's sort of organize that into a nice matrix because each of these variables exist for each month. And so here we are in a way that we can nicely read what's going on. Months 1 and 2, we're doing normal shift. Months 3 through 6, we're doing an extended shift. And so we're doing a shift every month. There's no kind of furlough of the factory going on. We change from a normal to an extended shift between months 2 and 3. And so that shows up in month 3. We kind of underproduce in the first 2 months. And so our inventory that starts off at 3,000 in month 0 dwindles down to 0 by the second month and stays at 0 with us just producing enough until month 4 we start or month 5 we start ratcheting it up so that we have 2,000 units by the end. Here's how much we're producing, and then here's the demand. The demand is a parameter there. I kind of just added it to the end to kind of give context to what's going on here for the demand. So that's it. Solution sort of makes sense. This is something I encourage you to do every time you solve one of these problems is, does the solution make sense? And yeah, this one, you can kind of tell the story of it and it makes sense. Would be hard to guess the story of what the optimal production plan would be without writing out the constraints and setting the computer loose on solving it. So that's it for this video.